Log on, tune in, find out. Another good idea from Cambridge.
To be honest, it's a pleasure to introduce George Petridis, who is going to tell us a bit about a new and less painful way of proving sum set estimates in abelian and possibly non-abelian groups as well.
Right, well, I would like to thank the organizers for the invitation. And like Tim said, what I'm going to talk about today, by the way, if those in the back can hear me, tell me I can speak louder. What I'm going to talk about is Plunnecke-type bounds on sum and different sets in groups. So these arise in the following context. Suppose that A is a set in a group, and we know that A plus or minus A is at most alpha times A. Then the question is, are there some good bounds on the cardinality of Ka minus La? Where of course this is the kth iterated sum set and this is the lth iterated different set. If somebody doesn't know what these things are, please tell me now. So yes, what I am going to do is present a new method to obtain this type of estimates that is simpler and in fact gives the best known bounds. I don't think they are the best possible. And having good bounds is important because this type of behavior is critical in obtaining some of the highlights of arithmetic combinatorics, like Feynman's theorem, sum set and product set estimates in finite fields, and many others. As Tim hinted, I will start by first concentrating on the abelian case. That is the one that these results are usually introduced, and hopefully I will have enough time to explain how the same method works for non-abelian groups. So let me begin by just going through as quickly as I can, what is known on the abelian case. Right, so the first such results were obtained by Helmut Plunnecke many years ago, over 40 years ago. What Plunnecke proved is the following. So suppose that A and B are sets in an abelian group. I'm sorry for this. And also suppose that A plus B are at most alpha times A in cardinality. Then there exists a subset X of A such that X plus HB is at most alpha to the H times X. So there are some things to say about this type of inequality. The first one is that it has more applications than one or two I talked about in my very short introduction. The second thing is that the proof is not particularly elementary. It uses graph theory, and it is somehow removed from what one considers an obvious way to prove these kind of inequalities. Hopefully I will say a couple of things about Plunnecke's original proof as well. The form that everybody perhaps remembers this is when we set A to equal B, and then we only have control on A plus A. Then we know that H times A is at most X plus HA, so this is at most alpha to the H times X, which is at most alpha to the H times A. I'm sorry for this. So this is the form that most people remember. Plunnecke's inequality is very symmetric, very easy to remember, and as I have said, it has applications. It is also yes, it is also best possible in terms of alpha. So what do I mean by this? So take A to be, let's say, a subgroup, and take B to be a collection of B, of mod B, generic points that lie in distinct subsets, distinct cosets, I meant. Then we know that A plus B is A times B. So in particular, alpha has to equal B. But for every set X in A, we have that x plus hb is b plus h minus 1 choose h times x. So that means that
Sorry, I have a question. Does this set X need another condition, or is there?
no, there is no other condition. It's actually a very powerful result.
Yeah, the point is that if x is too small, it's actually
Yes.
stronger.
Yeah, but X could be empty, right?
Yeah, but then it's stronger because on the right hand side you have 0.
Well, it's a non-empty. It is a non-empty.
It should be non-empty. Okay, so this is
Okay,
the
yeah.
minimal condition. Okay, but then
Both
it's
sides.
not-
Oh, sorry. I see what you're doing.
Okay, no
It's
other
empty,
condition.
but George H is empty.
But there's no other condition then.
What's the definition of A plus B?
The empty set, surely. Because it's the number.
Well, then it's also
something out
true,
of A,
right?
something
Okay,
out
that
of
is
B.
also true. Yeah, sorry. Yeah. Oh, so okay, so
Well, then the result has to be content.
The first thing we've got, second thing we've got is false.
okay.
The result is true.
Yeah, so in general, x will be non-empty. So does a and b. I think I have basically also my proofs, although I know that they can work in different contexts, I consider finite sets, a and b. So anyway, this kind of example shows you that one cannot really hope to improve the dependence on alpha too much. Now, what happened about 20 years after Plunnecke is that Imre Ruza basically rediscovered Plunnecke's theorem. And not only did he rediscover Plunnecke's theorem, he in fact rediscovered Plunnecke's proof. So the two proofs are amazingly similar. They're not identical, but they're very, very similar. But however, Ruza was also interested in difference of sets, and he introduced what is nowadays called as Ruza's triangle inequality. That is very, very simple. I will kind of hint how to prove it later on. But it is also very, very useful. So it's simple and useful. So suppose that we have sets u, v, and w in an abelian group. Then we have the inequality that u times v minus w is at most u plus v times u plus w. And what Ruza did is combine this inequality with Plunnecke's, or with his own proof of Plunnecke's theorem, and he deduced that when a plus b is less than alpha times a in an abelian group, then there exists x non-empty in A, such that x plus, I'm sorry, I didn't mean x, I meant kb minus lb is in mod at most alpha to the k plus l times x. Now, in almost all applications, one doesn't know anything about x a priori, so this is just usually written alpha to the k plus l times a.
Something must be. Should be an X involved somewhere else, shouldn't there?
No, I don't think so. No.
Why don't you just take X to be A then?
I can, yeah, but I mean, if x is a over 2, then you can get, I mean, if you know what x is. Okay, if you don't like it, you can forget about, let me delete it, it doesn't matter. Then this holds. So, this type of estimates, well, only makes sense if A and B have comparable sizes. Otherwise, bounding somehow a subset of B in sum that has to do with A is basically meaningless. And in fact, for the A, so yes, the most typical applications are when B equals A or minus A. This is what most people are interested in. And there is also an elementary approach that says the following. Suppose, again, in an abelian group that A plus A is at most alpha times A, then by methods very different to what Plunnecke used, but a little bit similar to Ruza because this triangle inequality is utilized, and also some covering lemmas that I'm hoping to speak later about, then A plus A is at most alpha A implies that Ka minus La is at most alpha to the k plus L times A. But this time I have to include an additional exponent, 6. So the elementary proof of these, they're called Plunnecke-Ruza inequalities, is somehow is a little bit more direct than what Plunnecke did, but it gives slightly worse bounds. Right. So I leave this board up so that everybody can see what the known results are somehow. And what I am going to do is present a method to get these sort of Plunnecke-type bounds. So, in fact, I combine the best of the elementary thing and of Plunnecke's original method. So they are elementary, as you will see. They're not very complicated, and they also give the best possible bounds, the Plunnecke bounds.
This elementary one is the one that's due to Terence Tao, is that right?
I read it in a book of Tao and Wu. Yes.
It is in that book. I think it's also in Terry's paper on non-commutative.
Oh, right. Yes, I have to agree with that, yeah. Anyway, yeah, the first time I've seen this is in the book of Tao and Wu. Right, so like I said, I'm going to present a method that proves Plunnecke's type of bounds that is elementary. In fact, it is slightly stronger. So here's what I'm going to prove. So again, let A and B be sets in an abelian group. And suppose that, as always, A plus B is at most alpha times A, then there exists a subset X of A such that for all H, Plunnecke's inequality holds. So X plus HB is at most alpha to the H times X. So basically, again, my proof will be different to Plunnecke's, and I'm proving something slightly stronger because the set X that Plunnecke and Ruza came up with, in theory, may have dependence on H. I will produce a single set that works for all H. This simplifies a tiny bit the deduction of this type of inequalities from Plunnecke's by using the triangle inequality. So I will still use the triangle inequality, but do it only a little bit simpler than what is customary. All right. Well, I have already placed enough importance on choosing an appropriate set X. So what I would like to do is motivate the choice rather than just write it down. And this brings me into stating more carefully Plunnecke's original theorem. So what Plunnecke did is he defined the so-called magnification ratios. So di is the minimum over all subsets Z of A of Z plus IB divided by Z. So he defined these quantities, and he proved that the sequence di to the power 1 over I is decreasing. So that's what Plunnecke did. So the way we are going to choose X, so we choose X that gives rise to the 1. Okay? So what does this mean? This means that X plus B divided by X is always smaller than Z plus B divided by Z for all Z that are subsets of A. All right? Now, to keep slightly, standard notation and also simpler, I will write this ratio as K and not as D1. It's just simpler is what most people do. So in particular, my choice of K means that Z plus B is always bigger than K times Z, again, for all Z that are subsets of A. Right, so I have told you now what set X I'm going to choose, and I would like to explain again, not motivate, but explain why it is a good choice. So I'm going to prove something like a proposition. For this X, Plunnecke's, the simplest instance of Plunnecke's inequality holds. So for this X, we have that x plus b is at most k squared times x, and by the way I have defined k, this is at most alpha squared times x. So this is really a special case of Plunnecke's inequality. Right, so let's see how the proof goes. I will just first of all draw a diagram. So the idea is to place, let's say, B somehow on the bottom layer. You can think of it as a graph, although it doesn't make any difference. Then you consider x plus b, and on the top you consider x plus b plus b. And you pass, of course, from one layer, from the first to the second by adding x, and from the second to the third by adding b. Okay, what I would like to do is partition x plus b in translates of x, all right? So we suppose that b is just b1 all the way up to br, some elements. The ordering is somehow important. So we have here b1, here b2, and all the way here br. Okay, so the first thing that I do is I just take on x plus b the set b1 plus x. Okay, that's a very simple thing. Now I want to do the same thing with b2. So I want to take b2 plus x. However, I'm not interested in the parts of b2 plus x that already belong here, because then what I want to do is I want to jump from here to there. So it doesn't really matter if I go like that or like that somehow, right? So what I am interested in, I will write this properly down, is b2 plus x2, where again x2 is a subset of x that has been chosen, so that this thing here is disjoint from that. And I carry on this way and choose in the end br plus xr. So let me write down something a little bit more careful. Then we choose xi that are subsets of x, such that x1 equals x, and for I bigger than 1, okay, we just simply choose xi to be the collection of x in x, right? Such that such that bi plus x does not lie in the union j equals 1 to I minus 1 of the sets bj plus xj, right? I hope that the combination of the picture and this will make clear what I'm doing. So again, b3, you know, there might be parts of b3 plus x that lie here or there. I forget about this and I just concentrate on the part that is somehow new. Right. So I will also write, this is just a notational thing, I will write as xi complement for the difference between x and xi. Okay, so now there is one more somehow elementary observation to be made, and it is the following. So we have that the union, when j ranges from 1 to I, of bi plus xi, this is in fact the union from j equals 1 up to I of bi plus x, and this is just the one all the way up to bi plus x, right? Again, the picture should convince you. And in particular, this means that the mode of, you know, when you take modes, the mode of b1 all the way up to bi plus x is the mode of this union. These are disjoint sets. So this is the sum j equals 1 up to I bj plus, I'm sorry, these are all j's, bj plus xj. So this is just the sum j equals 1 up to I of xj, right? And now I just make a simple claim that I will prove by induction. So the claim goes as follows. The cardinality of b1 all the way up to bi plus x plus b is at most k times the sum from j equals 1 up to I of xj. Right, once I have proven this, I will essentially be done, right? Why is this? We set I to equal r, okay? What happens then? The left-hand side is just x plus b plus b, and the right-hand side equals k times the sum of all the xj's, which is just k times x plus b, and x plus b is just k times x. Right, so if I establish this claim, then basically I hope I will have convinced you that you know, the set that I chose is a good one. And the proof is just like a very simple inductive argument. Right, so the idea is for I equals 1, we are done as x1 has been chosen to be x, and for I bigger than 1, well, we just have this that this is in fact by the kind of thing that I wrote up there. This is the union j equals 1 up to I of bj plus xj plus b, and this is at most b1 all the way up to bi plus x plus b, but here I'm sorry, I actually want to say bi minus 1, and then I have the remaining term bi plus xi plus b. By the induction hypothesis, the first term is at most times the sum of the xj's, where j ranges from 1 all the way up to I minus 1. And then this set is in fact the cardinality of bi plus x plus b minus bi plus xi complement plus b. So don't forget that xi complement, now I have deleted the picture, but the xi complement is the part that somehow lands in parts that we have already covered in here. And now we're basically done, because this is just k, the sum I is less than j of xj, and we know that this is just x plus b minus xi complement plus b, and this is just k times sum I less than j xj. X plus b we know is just k times x, and xi complement plus b is always bigger than k times xi complement. So adding these two together gives you just the sum, gives you the claim. And yes, that's all there is to it. And again, as Tim said, I mean, the usual proofs of these things are a little bit, I believe, in my opinion, a little bit more fiddly.
One of those last two equalities, an inequality.
This one, yes, you're very right, yes. This one. Here, because now I'm using the property that, of the definition of k here, right?
Well, and x, right? Well, yeah, sorry, yeah, yes.
Minimality, yeah.
And x, yes, and x, yes. So, what I have actually proved, okay, so there's a very important observation to be made. I hope you don't feel like I'm trying to cheat you or anything, but there is absolutely, in the argument, there's absolutely no reason why we should be adding the same set b to x 2 times, all right? In fact, what I have done works equally well, okay? This induction argument on the dimension of somehow the lower copy of b works equally well when I replace b with any set, All right? So, in fact, I have proved something slightly stronger, and I will state it here. So again, suppose that B and X are sets in an abelian group. Okay? Then, oh no, sorry, and also that we have this property that X is the set that somehow grows minimally under addition with B. So we have that X plus B divided by X is always less than Z plus B divided by Z. And this holds for all Z that are subsets of X. Okay? Then, for all sets C, we have the following inequality. We have that C plus X plus B is at most C plus X times X plus B divided by X. Alright, and now I will use this to inductively prove this slightly stronger form of Plunnecke's inequality. And as you might guess, I'm going to do it by first choosing X to be the kind of set that I have been discussing and then do induction. Okay, so this is proof of Plunnecke. So we choose X as before, so that means one that minimizes this expression here, and this implies that again C plus X. It implies that X plus B over X is at most alpha, right? Because that's the expression that is the minimum, and that's the ratio when Z equals A. So this means that the Plunnecke is okay for H equals 1, and then for H bigger than 1, you just do a straightforward induction. You have X plus HB is just H minus 1B plus X plus B. And what this is at most, from this contribution you get an alpha, and there you get X plus H minus 1B. So this is at most alpha to the H times X by the induction hypothesis. And that's all there is to it, really. Like I said, there are few instances where actually having the same set X that works for all H makes a difference. I mean, I have used this kind of thing once. But there are many instances where if you want to use, Plunnecke's inequality in your research and stuff, that writing down the proofs can be simpler if you use the same set. So to demonstrate this, I will deduce those inequalities of Rusa by the stronger form of Plunnecke's inequality. So now let's deduce Rusa, and I will first say something about his triangle inequality. By the way, it's called a triangle because one can define the distance between two additive sets in some sort of way, and then this inequality helps one prove that what you have actually satisfies the triangle inequality, so it's something like a metric. So let's remind ourselves what Rusa did. He said that U times V minus W is at most U plus V times U plus W. And the way to prove this is actually very, very easy. You just construct them, if you know how it goes, right? So you construct a map from U cross V minus W to U plus V cross U plus W. And this is the most simple map you can think of. So you take U V minus W, where this is somehow a unique representation of the element here, and you take this into U plus V, U plus W, and I won't show it here, but this is an injection, and that's just the proof. So this actually very useful inequality in additive combinatorics has a one-line proof or two-line proof or something. So now let's just see what happens when we apply it for the set X that I have already chosen. So we have X, and then you have KB minus LB, right? is at most x plus kb times x plus lb, and the first term is at most x times alpha to the k, the second one is x times alpha to the l. The x's cancel out, and that means that kb minus lb is at most alpha to the k plus l, and I also bound x with a. And I have proven these so-called Plunnecke-Rusa inequalities. Right, that's all I have to say about the abelian case. Seeing that I have time, I will use a little bit of what is left to discuss Plunneke's and Rusa's original graph theoretic argument. I won't go into any detail at all. I will just present it very quickly, as I have found a way to simplify these two. And for those of you that know it, actually,
So you got two sizes of x.
yes, but I started with one here.
Oh, there is not.
Yeah, I'm sorry.
Thank you.
Right. So again, let's just. What I said already is that Plunnecke did use a graph theoretic method. So what he did is he thought of layered graphs that are somehow directed. So they are directed and layered. So he put A again in the bottom, he put A plus B in the next layer, and A plus B here. And then he passed somehow from one layer to the next by adding B. Right, so it is important actually to do things in that order. So anyway, I hope you can see that there is a B here somewhere. But anyway, it is important to actually add the same set when you pass from one layer to the next. And again, let's remind ourselves to define the magnification ratios to be something like the minimum over all z in A of z plus ib over z. And he proved that the sequence di to the 1 over I is decreasing. Right, so if you think about it in terms of this graph, I think if I try to explain, I will make it harder than it looks, so I will not. But a little bit of thought, either now or in your spare time, will convince you that basically magnification ratios. Oh, sorry, okay, I take this back. Let's start on another. So what actually both Plunnecke and Rusa did, again 20 years apart independently, is that they first established the case when dh equals 1. Okay? So they showed that if you assume that the last magnification ratio is 1, or in fact bigger than 1, then you have that all the magnification ratios have to be bigger than 1. I mean, that's not exactly something like this, but it's a first step towards it. And to establish this, what they did is the following. So they worked again in this graph, and they noticed that magnification ratios are really the same thing as sets separating A from A plus B plus B. So for the graph theorists among you, it's like a set separating the bottom layer from the top layer. And this, of course, screams something like Menger's theorem. So by applying Menger, they saw that there is some close relation between magnification ratios and vertex disjoint paths in the graph. And what they were able to do then, with again a roughly speaking similar argument, is use the somehow commutativity So they use the commutativity that exists in the graph. I won't even try to explain what this is, but there is some sort of commutativity. Because if you are in A, and you go to A plus B, and then to A plus B prime, you can also follow an alternative route a plus b prime, a plus b, this kind of thing. So they use this to deduce that under the assumption that the final magnification ratio is 1, that di has to be bigger than 1. Of course, they were anything but done at this stage. And what they did is then they deduced the general case of Plunnecke's inequality by the so-called Cartesian or tensor product. So they considered the product of G with itself. Not with itself anyway, but so they used Cartesian products of graphs. To deduce the general case, so the case that works for all the A's. Right, so what I observed at some point is the following thing, that when one thinks about separating sets, it is better to not concentrate on disjoint paths, but rather on the following very, very simple observation. So when you have a set S here, okay, this is somehow a minimal separating set if both the image of S and the inverse image, so you can think of the image as the neighborhood or something like that. So this is the vertices that can be reached from S, or the vertices that lead into S have smaller cardinality than S. So again, what did I observe? That S is separating if and only if both the image of S and the image inverse of S are bigger than S. And surprisingly enough, such a simple observation is enough to, so this is enough to prove Plunnecke's inequality. Or the version of Plunnecke's inequality when the H equals 1. Okay? So somehow in theory I would still need to apply this kind of Cartesian product that is a little bit nasty to explain. But by just giving weights to the different weights to the vertices of G, so that somehow, you know, when there is no weight, you assume that the weight of everything in the first layer is 1, on the second is 1, on the third one is 1, but one can in fact give different weights. Leads to a proof of the general case. And this proof, like I have said, does not use Menger's theorem and does not use Cartesian products of graphs. I still have 10 minutes to go, 20 minutes to go. I will try to finish 5.2. So I want then to explore a little bit what happens in the non-abelian case. All the things that I said about these graphs rely on that commutativity property that I have now re-raised. So they are absolutely not applicable. However, there are still things that have been done. And there is another observation about this theorem that I proved here. At the time I didn't, hammer the point, just to make everything more clear to you. But in fact, everything that I wrote down with a plus can be replaced with a dot. So I did not use commutativity at any point. So that means that this technical looking theorem also holds for the non-abelian case. So just like before, I will start with a brief explanation of what is known in the abelian case. So the first thing that is perhaps a little bit, shattering news is that Plunnecke's inequality simply doesn't hold in the non-abelian case. There is a very easy example, and I will present it. Right. So take A to be the union of a subgroup H with a somehow generic element X. Okay, now because I'm in the non-abelian case, I will start writing with dots instead of classes. A dot A is at most X dot H plus H dot X plus X dot X. And this is at most 3 times A. So if Plunnecke's inequality held, then what we would have is that A dot A. Yeah, please.
Plus H.
Oh, whoop. You're very right. Yeah, you're very right. I'm sorry, I forgot one of the most important terms. H dot H.
You can omit the x dot x, can't you? Or no?
I don't. And this is at most 3 times A still. Yes. Thank you for this. So then, if Plunnecke's inequality held, what we would have is that the triple product would be at most 27 times A. However, the triple product includes the set H dot X dot H. All right? And there are examples, they're not too hard to construct, where somehow this has order, this is exactly of sides H squared, that is A minus 1 squared. So you have some sort of linear factor on the right-hand side and some quadratic factor on the left-hand side. So obviously, this is a mistake. This is impossible, and that means that Plunnecke's inequality, like we stated it, does not hold. Right. There are, however, generalizations to it. What I mean by a generalization is if extra conditions, or if things are done a little bit differently than the abelian case, and the different way of doing things or the extra conditions would be completely trivial in the abelian case, but are non-trivial in the non-abelian, and then useful conclusions can be deduced. I will present the 2 examples that I know of. The first one is of Terence Tao. So again, what Tao did is he considered a set A in a group, so not necessarily abelian, and then he assumed that 2 things are somehow bounded. A dot A is at most alpha times A, and also A dot little a dot big A is at most alpha times A for all little a in big A. The example that I presented above shows that this second condition is necessary if you want to get something like Plunnecke-like looking. And I believe that the first person to kind of suggest that something like that would be useful is Imre Ruza. And what Tao did is he deduced that the triple product is at most alpha to some constant C times A. Now, C is a relatively large constant, it's at least a digit. It's not 10 to the 10th or anything like that, but it's slightly large. And of course, it is important to know that once you have triple products, I will not cover this, but once one has this type of control on triple products, then by the triangle inequality of Ruza, that also works in the non-abelian case, you can prove that the H-fold product set has some sort of Plunnecke-type bounds. So this is Tao's theorem, and Ruza has done something slightly different. So, in the abelian case, I would say that instead of looking, I'm sorry, I don't mean x plus b, he looked at b plus x plus b. So changing the order of the summands is trivial in the abelian case, but not so trivial in the non-abelian. So again, what did Ruza do? Is the following. So he took sets A, L standing for left, R standing for right in a group, and he assumed that we know how A behaves when multiplied by L on the left, and how it behaves when multiplied by r on the right. So the first product is at most lambda times a, and the second one is at most rho times a. Then he was able to prove that there exists a subset x of a such that L dot x dot r is at most lambda rho times the cardinality of x. Again, a couple of things about his proof. The first thing is that it is a direct consequence of the graph theoretic thing of Plunnecke that I kind of discussed a little bit, although I will not explain how. And the other thing is that having this type of so the example I first presented shows that having this type of theorem is not enough. Is of course not enough to say something about a dot b dot b, about x dot b, I'm sorry, about x dot b dot b when a dot b is known in terms of a. So right, that's simply not the case. And to compare what we have just proved with Rusa's theorem, I will state it also here. Okay, it's slightly different, but again, let A and B be sets in any group. Then there exists a subset X of A such that for all set C. Oh, I'm sorry. And I also need to assume that A times B, the usual thing, is at most alpha times A. I'm really sorry I've forgotten this. So they are sets that satisfy this somehow small doubling property. Then there exists a subset X of A such that for all set C we have that C dot X dot P is at most alpha times C dot X. So this is what we just saw how to prove. This is strictly speaking weaker than Rusa's theorem. However, it is perhaps a little bit easier to apply because you can use again the same X for all set C. I mean, there is some application. I don't think I'll have enough time to go into it. I want to devote the next few minutes into a proof of Tau's theorem, where the constant little c is specified. Correct? So Tau's theorem is the one there. So I want to prove Tau with little c equals 8. I won't prove it, I will just explain how to do it. So basically, I will use the two most commonly used tools in additive and arithmetic combinatorics. So the first one is the triangle inequality. I won't explain it any further, but it says that in any group, u times v times w, sorry, the mod of u times the mod of v times w is at most v u inverse times u w, right? So this is slightly different than what I had written before, but
Tau's inequality is not ineffective, is it? I mean, he does get an explicit value.
yes, absolutely, yeah.
What value C does he get?
I haven't really checked it. I mean, I started off, I can guarantee to you it's more than 20, but now whether it gets to be 100, I don't know. It's still relatively large, as I said. Also, the other thing about Tau's argument, to be fair to his argument, is that he wasn't really trying to prove only this thing. He was doing some sort of more general classification. That means at some point he says, well, let's use that proposition, and it takes a little bit of thought to understand whether his argument in the proposition can be somehow a little bit more economical in the case where you just are interested in triple products. It was, though, a question of Rusa to determine an explicit constant. It's also surprising that you don't need the theorem that I just proved. You can actually do it with Rusa's theorem, although you get little c to be 9, I believe. But anyway, these are just constants. So basically, I'm going to use, again, the triangle inequality and the covering lemmas. So the covering lemmas, that was the second ingredient in obtaining the elementary proof of Plunnecke's inequality in the abelian case, right? That I have already raised, but they were somewhere up there, I think. So what does the covering lemma say? It says that suppose that u times v is at most alpha times u, then there exists a set S that is a subset of V of size at most alpha, such that V is included in the triple product U inverse dot U dot S. Okay, so we'll use these two ingredients to deduce Gauss theorem. Right, so again I choose X in A that minimizes the ratio Z dot A over Z. Okay? This is what I have been doing all along. And then I want to apply the covering lemma. So what we know is that X dot A is at most alpha times A, and that means that there exists a set S in A of size at most alpha. Such that A is included in the triple product X inverse X S. Okay, and this immediately gives me an upper bound for the triple product A dot A dot A. So this is at most A, X inverse X S A. Okay, and this is the moment to apply the triangle inequality. So what I want to do somehow is insert an A here. So how this is done is that I get A X inverse X A inverse times ASA divided by A. And now I will compute these two terms I want, but I will explain how to compute them separately. So on the first one, I will just basically, I won't do it, but one can just repeat the triangle inequality enough times to deduce that a bound on this basically depends on a bound of something of the form A X A. Okay? And at this stage, you either use what we proved today or Roux's theorem to bound this triple product. So using the triangle inequality will never solve your problems entirely. You need something stronger. So by what I have proved, this is at most alpha times X dot A. I'm sorry, A dot X, which is at most alpha times A dot A. And by the first condition, this is at most alpha squared times A. So combining this calculation with something, with some other applications of the triangle inequality, one can get that the first term is at most alpha to the sixth times A. Now we're just left with the second term that will be computed using the second condition. So again, we have to bound A dot S dot A. This is just divided by A. So this is 1 over A times the mod of the union little less and bigger, A little less A. Okay, so this is at most the sum over all S in S, ASA divided by A. And now it is important to note that the set S is a subset of A. So we can in fact use the second condition in Gauss theorem to deduce that this is at most, there are S summands and this ratio is at most alpha for each one of them. S is at most alpha, so this is at most alpha squared. Okay, I hope I haven't tired you out completely, but this means that A dot S dot A is at most alpha squared, and putting everything together gives this bound of 8. And before I stop, I should say that if you're interested in multiple products of in the H-fold product, then it is better to combine this type of theorem where C plays the role of the set that you want to do the induction hypothesis on, rather than just use Tau's theorem on the triple product and the triangle inequality. So let me say this again, that in certain occasions, so yeah, if you want to take bounds on a to the h, it's better to use some sort of inductive argument, what we have proved as the first step, then the triangle inequality, and then what I have proven here, where C helps you do the inductive step. I think I have said enough, and yes, I think I will stop now. Thank you.
Does anybody have any questions? Do you know what the constant is, what the actual result is for the bound for A?
Yes, under these conditions, I think, so the h plus 2 full sum, I think is something like alpha to the 9h times A. So it turns out that you have to, something like that. But again, with the triangle inequality, just you need to have something like 18 or 16 here. It's not a big deal. But yeah. All right. Okay. Well, I think I'll step down. Any more questions?
Let's thank the speaker again.